In this video, we're going to look at Azure Data Explorer, a big data service that allows the collection and analysis of data from any number of sources. Some of the more common sources for Azure Data Explorer are websites. Any data collected by a website can be sent to Azure Data Explorer programmatically via an API, for instance, and collected for analysis. Applications can likewise programmatically send data for ingestion to Azure Data Explorer, perhaps as aggregated data from various calculations. And physical IoT devices can stream their data to Azure Data Explorer. These are only a few examples. Due to its extendability, there's really no end to the data sources for Azure Data Explorer. And once the data is collected from the source, you can use Azure Data Explorer's Kusto query language, which allows analysis queries to be run in seconds on huge datasets. Now let's look at some of Azure Data Explorer's many features. It scales very quickly, which is ideal for ingesting large data. Do you need to query terabytes of data? No problem, because Azure Data Explorer can run analysis on such datasets in minutes. It uses Microsoft's innovative Kusto query language, which is ideal for high-performance queries and offers standard analytics features. Under the hood, it's NoSQL, allowing for heterogeneous data, and Kusto allows you to analyze these datasets very quickly. It's extensible programmatically and also interfaces with many services in Microsoft's Analysis Suite of services. So you can include it in your custom architecture and build and deploy whatever you need. Azure Data Explorer is a complete data warehousing and analysis solution. Let's look at its workflow. It starts with collecting the data. This can be done in many ways, but some common data collection services in Azure are IoT hubs for data from IoT devices, Event Hub for serialized events, and even custom services. Some examples of the media to temporarily capture this data are blob storage, table storage, or Cosmos DB databases. Then the data is ingested into Azure Data Explorer. There are built-in data connectors for common collection media, such as blob storage, although you can also programmatically create your own service for this. Azure Data Explorer stores the ingested data internally, and then it has efficient indexing to support real-time analysis of structured and non-structured data. Kusto allows querying of potentially terabytes of data real-time, and Azure has visualization options such as Power BI, which can display the results of analysis. So how does Azure Data Explorer work from the point of view of someone wanting to analyze the data? Well, the flow goes like this. First, you need to create somewhere to store the data. So you create a cluster, which is an instance of an Azure Data Explorer resource. Then you create a database within that cluster. Next, you ingest or load the data into tables in that database. You typically set up a mapping that automatically ingests collected data once it arrives into the system. For example, if you're ingesting from blob storage, you can set up Azure Data Explorer to ingest blobs from storage as they're created. And finally, with the data in the database, you can perform your analysis via read-only queries. An important detail is that data is never deleted or modified in Azure Data Explorer, unless a service, such as Azure Data Factory, is used to archive it for offline use outside Azure Data Explorer. As mentioned, querying is a read-only method for processing data in Azure Data Explorer. The Kusto query engine allows querying in many fashions. You can always query data stored in a column store by columns. If the data is free text, or even if it's structured, you can take advantage of its fast text indexing to look for patterns in strings, such as log details, for example. And there are built-in time series operations for time series analysis. This is particularly useful for analyzing the time series data that comes from IoT devices, which is a popular use of cloud technology these days. Azure Data Explorer, and particularly the Kusto engine, are used by many of Microsoft Azure's core services. In this way, Microsoft has been testing and perfecting this technology for years. Some of the services that use the Azure Data Explorer technology under the hood are Azure Application Insights. Just about all of the core services in Azure have the option of monitoring via Application Insights. Insights can be gleaned from all that information by performing Kusto queries. This is a great help for debugging your Azure services performance. Azure Monitor Logs is another in the Azure Monitor suite. It allows your services to log important information such as usage and performance data. And again, it's all queryable with the same Kusto engine. Time Series Insights is a service specifically for offering real-time analytics on time series sources, such as IoT devices. It's feature-rich and designed to offer most of the features that users of a time series data analysis platform would expect. And there's Windows Defender Advanced Threat Protection, which collects an array of data from your virtual system to give you real-time threat protection advice. It does this by internally querying data stored by Azure Data Explorer. In this demonstration, I'm going to show you how to visualize data from Azure Data Explorer. Now, Microsoft hosts a public UI for Azure Data Explorer, which I have open on the screen right now. To view it yourself, go to dataexplorer.azure.com. Now, this UI can connect to any Azure Data Explorer cluster, so you can create a new Azure Data Explorer resource in Azure, and you can enter the connection URI to access your data via this UI. Luckily, Microsoft offers a test cluster that we can use for this demonstration. So I'm going to click Add Cluster, and the URI that you enter for that cluster is https://help.kusto.windows.net. Now, Kusto is actually the query language that we're going to be using. And for display name, I'll just call it test data. Click Add. So you see under Add Cluster, we now have test data listed. Now, if I open that up, it has a database called Samples, and that database has a bunch of tables in it. Interestingly enough, it has COVID-19 data, it has geospatial data, and today we're going to query the storm events data. So the first query I'm going to show you is just querying that storm events table. And unlike SQL, where you have to enter a select query, in Kusto, all you have to do is give it the name of the table, and you can ignore the underscore. So I have to also set the scope, so I have to highlight the database that I want to query. Now, if I run this, what you're going to see at the bottom right is it says how long this is running. Now, you notice this is taking a long time. That's because this is a large data set, a very large data set. So I'm going to cancel that. And what I'm going to do, and you can see at the bottom, it actually has brought back some data. But what I can do is I can limit that and say 10,000. And that tells it to take only 10,000 records. Now you notice that only took a few seconds. So this is really designed for very large data sets. Now the next thing I'm going to do is I'm going to limit this storm events query because what I want to see is records that represent heavy rain. There's an event type field in here. If I just scroll the table to the right, there's an event type field, and one of the values that can be in that field is heavy rain. So on line 2, I have the pipe, which you use in Kusto to add details to your query, where event type, and the double equals is a Boolean equality sign, and I'm searching for the string heavy rain. So now when I click Run, I see the details, and these are all heavy rain event types. And I can see that there's 836 of them. It also shows what state they're in. So what I'm going to do is I'm going to summarize these details, and what that means is to take the results and aggregate them somehow. And I'm going to aggregate by state, and I'm going to take the count of records per state, and I'm going to call that event underscore count. If I run that, you now see that I have 2 columns in the table. One is the state, and one is the event count, and that's how many heavy rain events have been in that state throughout the whole record set. Now the next thing I'm going to do is I'm going to render that as a column chart. And this is one of the great things with Azure Data Explorer is it can actually render different charts. So on line 4, I go pipe render space column chart. And if I run that, if I will just take out line 4 again and just run, remember that state is the first field and event count is the second field. So the first field will be the x-axis value and the second one will be the y-axis. If I just put that back, the render column chart, and hit run, you see that the state is at the bottom and the y-axis is the number of heavy rain events. So you can see right away, and you can actually hover over them and see the details. So I can see Kansas is highest at 107 events. So in conclusion, what I've shown you here is how to access Microsoft's UI for Azure Data Explorer, connect to an Azure Data Explorer cluster, query that data, and even visualize the data in a column. The data reporting technology that you choose to use has to meet the report user's purpose. And in many cases, data analysts are your primary report users, and they'll have specific data analysis requirements. In this video, we're going to look at choosing the proper data analysis tools for your reporting needs. We'll look at the main technologies offered by Microsoft, and we'll also discuss what the primary goals of data visualization and reporting are, and the main tasks and responsibilities of a data analyst. We'll finish off with the key criteria that you should consider when choosing your data reporting technology. To start off, let's talk about what Microsoft Azure offers as far as data analytics technology. In some cases, all that's required are pre-configured reports. These offer the analyst a standard summary of the dataset. There's no input on the data analyst side. The information is simply summarized for them. These pre-configured reports often include visualizations such as charts to summarize the data and highlight important trends in it. Reports can also be interactive. These allow the analyst to interact with the report. So for instance, they might be able to enter factors into the report to see results when they're combined with the dataset. Or analysts might be able to filter the data as a tool to find patterns in the data. Interactive reports can also include visualizations for data summary. So let's break down what Microsoft Azure offers in terms of data analytics technology. First, there's Power BI. Power BI is focused on business reporting, and one of its big strengths is its ability to collect data from a large variety of sources. Most data sources in Azure can be consumed by Power BI, which allows analysis to be run on the dataset and the data presented in reports with built-in visualizations. Power BI relies on Azure Active Directory for its authentication and authorization. It allows data analysts to run ad hoc queries, and it can be embedded into other applications. Jupyter Notebooks is a tool that allows you to run Python, Scala, or R code for analysis, and it comes pre-configured with many HD Insight clusters. Zeppelin Notebooks is another tool that's similar to Jupyter Notebooks. If you're running HD Insight Hive queries, Zeppelin Notebooks is currently the only technology available for you. And finally, Azure Notebooks takes a solution based on Jupyter Notebooks to the cloud. Where Jupyter Notebooks normally uses data from an HD Insight cluster, Azure Notebooks is not paired with a default data source, and so you must pair it with a source. Many Azure sources can be used, such as blob or table storage or SQL database. So what do data analysts use data reports for? Let's take a look at some of the common data analyst goals. Data analysts are usually not interested in individual data points, but instead are trying to determine trends in the data. They usually do this by combining data from disparate but related sources. As a simple example, if a data analyst is looking at the output of an HVAC unit that controls the indoor temperature of a mall, he might want to find the most efficient settings for the HVAC over the course of a year, and he might do this by combining the yearly HVAC electricity cost with data on the weather and real-time occupancy of the mall to see if there are any trends in season and occupancy that affect the cost of running the HVAC unit. Data analysts are also responsible for identifying issues by looking at these trends. They may know what they're looking for, but interestingly, they may not. They may find issues that they didn't even know existed. While analyzing the HVAC data from the previous example, a data analyst might notice that the HVAC unit is particularly inefficient at a certain time of day, and they might have to dig deeper or even look at other types of related data to find out why. In general, the data analyst is looking to gain insights from the data, so data visualization and reporting must support this goal. Now that we've discussed some general goals of the data analyst, let's look at what they do in a little more detail. Data analysts are trying to make complex data more accessible. The value of their work is not in the analysis itself, but in the findings, and in their ability to present those findings to the business. They'll often create visualizations such as charts to achieve this. Integrating data is also important. As the HVAC example shows, data trends often involve aggregating and comparing different types of data. And data also often needs to be combined from different sources. Data analysts do all this data manipulation in order to find patterns that give them business insight. And finally, a data analyst must present this information in a meaningful way to the business. Now let's look at some common tools that help data analysts do their jobs. The first is Power BI. This is Microsoft's solution to visual reports and ad hoc analysis for data analysts, and it consists of several services that work together. Its big advantage is that it can connect to hundreds of data sources, such as Microsoft Excel, or cloud data sources such as Blob and table storage, or cloud-based SQL Server databases. It's designed to allow the data analyst to discover important trends in the data by defining their own visuals and performing ad hoc analysis. The data analyst can also use Power BI to produce and publish reports of their findings to share with others in their Azure Active Directory. Where Power BI is more query and filter based, Jupyter Notebooks allows data analysts to analyze data using what's called a notebook that's programmatic. They can use Python, Scala, or R code to customize visualizations and process data in novel ways to gain insights. Zeppelin Notebooks works much like Jupyter Notebooks, but it specifically works with Hive queries, and you can also assign different user logins to control authorization based on an HD Insight cluster domain. Like Power BI and Jupyter, Zeppelin Notebooks have a browser interface. Azure Notebooks is essentially Jupyter in the cloud, allowing an array of cloud-based data sources. It's free, it's easily accessible without a local install because it's a cloud-based service, and you can share your notebooks with others in your Azure Active Directory. So what are key points that you need to consider when choosing data analytics technologies? First, you need to consider whether the data analysts that are going to use the technologies are going to require data from multiple data sources. In most cases, this will be required, since analysis often requires data from disparate sources to be effective. Are you going to want to embed visualizations, such as charts, in with your own applications? Are your reports going to be consumed completely online, or do you require offline reports? I've personally helped design report systems, and we had to consider not just who would receive offline reports, but how we might secure them so those who were not authorized could not read them. And you need to consider the size of the data sets that will be involved. Do you require big data clusters? These key criteria can help you select the correct technologies. And remember to review these criteria once in a while moving forward, since your organization's data analysis needs will likely evolve over. In this video, we're going to look at SQL Server Reporting Services, or SSRS. SSRS is not one but a collection of tools and services that run on premises. SSRS can be used to create rich, customized reports based on SQL Server database data. SSRS also contains services to deploy reports to the right people. Further, SSRS can deploy reports on different platforms, including web-based and mobile. It also offers flexible pagination. And finally, SSRS helps manage those reports and the permissions to them. So let's talk in more depth about the different ways SSRS can deploy reports. It simplifies creating reports by offering powerful and modern pagination tools. Pagination templates can be created to allow generation of multiple pages based on the dataset. Everyone expects information at their fingertips today, so SSRS displays rich reports on mobile devices with responsive layouts for easy reading. An SSRS report server can expose a web portal that allows for display of reports over a wide range of compatible web browsers. It also allows for management of reports, report scheduling, and report history. Recently, the reporting services of SSRS have been updated, so with minimal work you can get the most modern-looking and effective reports. Different popular reporting tools offer different features, so SSRS allows for hybrid reports, which can mix both standard SSRS report service objects with Microsoft's Power BI tool in one report. As a report manager, you want to impress your customers, but you don't want to spend a lot of time customizing your reports. So SSRS has offered many updated styles. So one of the many standard report styles is likely to suit your needs with minimal modification. The SSRS interface is constantly being updated over time, and one of the recent changes that users wanted was parameter lists that are customizable. Format is a big deal with reports as well. PDF format is very popular for reports, but offers minimal interaction, and some customers want interactive reports. Recently, SSRS has expanded their export formats to include such formats as PowerPoint, and the exported PowerPoint can be interactive. So for example, a user could modify filters on a page to see different results. As mentioned briefly, mobile reporting is huge these days. Everyone has a mobile phone, and they expect to be able to view their reports. I've been working with reporting software since before there were common standards for reports on a phone, and in the past we would double our development by creating different versions of the report for desktop and mobile devices. Now there's HTML5 and responsive layouts that make offering a mobile experience far easier. SSRS now allows a SQL Server migration assistant that takes reports from the popular DataZen platform and formats them for mobile use. There's also a mobile report publisher app that allows you to create new reports that are optimized for mobile devices. Users can consume these reports with the Power BI apps available for mobile devices. Now, if you don't want or need your reports to be delivered via a native mobile app, you can also use the reporting service web portal. This portal is exposed by SSRS servers that are in native mode. It offers reports that can be paginated on mobile devices via the device's web browser. These reports can feature your main KPIs, so the report serves as a quick summary. If someone is in a hurry, they can see the important numbers without cracking open the full report. This web portal is HTML5 compatible and works with all the major browsers. You can store all sorts of data sets and data sources in the portal environment, such as Excel workbooks and other data sources. It also allows those with the right permissions to manage and administer what's shown on the SSRS reports, so administrators can do their job remotely as easily as regular users can view their summarized reports. Now, so far we've talked about the built-in features of SSRS, but SSRS also has a programming API surface that allows for reports to be extended and customized. Because functionality can be programmed, your company can offer reports that suit the most finely detailed customer requirements. The APIs allow control over the data used. So even if you use custom data sources, you can integrate your data or even aggregate and extend the data. You can also perform custom reporting processing to suit your reporting workflow. With these powerful programming capabilities, SSRS becomes not just another reporting tool, but actually a reporting platform that you can extend to suit your own needs. In this video, I'm going to show and discuss some of the different chart types that are available in Microsoft SQL Server reporting services. Charts should make it easy for the user to see the significant patterns in the data. So it's very important that you use the correct chart type to highlight the desired data patterns. Now, first note that I'm showing you chart images from the public Microsoft documentation, so feel free to look these up and view them yourself online. So the first chart type that I'm going to show you is the area chart. Now, area charts show a filled area under a line, so they're good for showing aggregates such as sums over time. What you see here is what's called a stacked area chart. This shows several categories stacked on top of one another, so you can get the idea of the total sum as well as how the individual sums compare to one another. Next, we have a bar chart. Now, like the stacked area chart, this is good for comparing different categories beside one another. And it's shown horizontally, so the value being compared between categories is actually the x-axis. In this case, you see it's money. And the y-axis is often time. The different colored bars themselves are the actual categories. If you're showing category values over a short, finite time, this is a very useful chart. Next, we have a line chart. Now, line charts are good at visualizing a lot of time-based data. In this case, each category is shown as a different line, so you can compare their relative values over time. For instance, you can see that in Q3, Japan had a higher value than the US. However, you can quickly see that in Q1 it was reversed. Now, a line chart is really good at summarizing a large amount of data. Each of these categories could have thousands of values over this given time range. But summarizing all those points as a line is a way to visually summarize the data trend. Next is spark lines. Now, spark lines are like mini area charts without any axes or other details. As you see, they show the current value on the left here, and then the line and area give you an idea of the overall trend over the most recent time, such as the last hour or the last day. Now, these can enhance single values by showing that trend. So, for example, the value could be the number of sales for a salesperson for the day, and the trend line adds useful information by showing that salesperson's sales trends over the past week. Next, we have pie charts. Now, pie charts are a comparison of an aggregate of categories as a percentage. Note that there's no axes, and this is not over time. The important information here is what percentage of the whole each category represents. So in this example, we can see that of all lunch sales, 20% of those lunch sales are salads. Some examples of when a percentage breakdown like this could be useful might be in a breakdown of nutritional information for food or a grade breakdown for a class. Next, we have a scatter chart. This shows data points as individual dots across an x and y axis. Now, in this example, the x-axis is time, but it doesn't necessarily have to be. This chart can be really useful to show the interaction between two important properties when they're used as the x and y axes of the chart. Next, we have gauges, which are used to show a current value and how it relates to an expected range. Now, a common gauge is the gas gauge in your car. You care about how much gas you have at the moment, and you don't see history, but it shows you your gas level in relation to empty and full. Now, there are different styles of gauge which are largely personal taste. You see here there's a radial gauge and a linear gauge. They show the same information but in a different style. Now, the next one is a very specific type of chart, the stock chart. For stocks, the important details are typically the range over a time period, the starting value, and the closing value. Now, in these types of charts, the range is shown as a vertical line. You can see each of these points is a range of time, perhaps an hour, and the vertical line of each of these points shows how much it's varied over that hour. Now the start value for each of these points is shown as a left tick, and the end value is shown as a right tick. Note that by looking at these ticks, you can instantly see whether the stock rose or fell over that 1 hour period. Now with the correct chart, huge data sets can be summarized in a way that makes it easy to see relationships. What you're looking at now is a tree map chart. The tree map chart shows categories by different sized rectangles and colors, and also shows subcategories within those categories in the same way. This particular tree map is a breakdown of bike sales by territory. Now just by quickly looking, you can see that the Southwest Territory is the best selling because it has the largest rectangle. And you can also immediately tell that the Southwest best selling bike is the road bikes because that's the largest rectangle within that rectangle. So this is a way that a lot of complex data can be very quickly summarized for the eye. SSRS also allows you to show maps. Now this is a map right here of Washington State households by county, and then it shows bubbles on the map to show the values. This is useful when it's important for the user to understand the geospatial details of your data. So in conclusion, SQL Server Reporting Services offers a large range of chart types that are suited for different types of data. Choose chart types wisely. A chart should allow the user to see the data trends that are most important in that dataset. Charts should enable your reports to summarize large data sets into concise, meaningful images. Data analysts are not really interested in the data, but instead what insights the data holds. There are various analytic techniques you can use to find those insights, and in this video we're going to look at those techniques. We'll look at the following techniques: Descriptive Analytics, in which the analyst highlights what happened in the past; Diagnostic Analytics, in which the analyst determines the reason for past data trends; Predictive Analytics, which attempts to predict future data trends; and Prescriptive Analytics, which gives you ways to affect future outcomes. We'll also touch on Cognitive Analytics, which relies on learning computer systems that attempt to analyze data in the same way a human might. So first, let's look at Descriptive Analytics, which is determining past trends in data. This is one of the simplest forms of analytics, so it's often one that is utilized first by young companies. I've personally helped create several services to perform descriptive analytics on data. Descriptive analytics simply looks at data to see what happened in the past. An example of this would be KPIs of last quarter's sales figures on a report. It doesn't draw conclusions on the data, but instead simply summarizes and presents it for its inherent value. Although simple, descriptive analytics can help assess business performance by using graphs, charts, reports, and dashboards. For instance, a simple line chart can show the growing or shrinking sales patterns for an organization for the past calendar year. Diagnostic Analytics takes descriptive analytics to the next step by not simply exposing the past data patterns, but helping the data analyst to determine why those patterns happen. This can also be called root cause analysis, because it exposes a root cause of data patterns. Some common aspects of diagnostic analytics are data discovery, which is focused on the collection of data from various data sources to facilitate analysis; data mining, which is digging into that collected data for meaningful patterns and insights; drill down features in reports, which allows the data analyst to move from general information, such as a table of the sales statistics of all regions, to a more specific view, such as the sales statistics of one specific region when you click on that region in the general report; and also drill through in reports, which allows the data analyst to move through different visualizations of the same data set, such as allowing them to click on the table of sales statistics of all regions in order to go to a geographic map of those regions with the same sales statistics shown. Next, we have Predictive Analytics. With Descriptive and Diagnostic Analytics, past data trends and patterns are identified and analyzed. Predictive Analytics takes this a step further by applying those data insights to predict outcomes in the future. The idea here is that past trends will predict future trends. And the next step is prescriptive analytics. Taking the prediction of future trends from past trends that are garnered from predictive analytics, prescriptive analytics endeavors to determine the appropriate courses of action based on the future predictions, and outlines the potential implications of taking each. With this form of analytics, an organization can take action to improve their future business. For example, an organization might have used descriptive and prescriptive analytics to determine that their HVAC units were inefficient in humid conditions because of a weakness in the design. Now, prescriptive analytics can give them potential courses of action, such as correcting the weakness or adjusting configuration of the existing HVAC units to compensate. Prescriptive analytics should give them an idea of how the HVAC efficiency will be affected over time if they take each of those possible courses of action. An exciting new field in analytics is cognitive analytics. This is applying human-like intelligence to make decisions. Artificial intelligence has come a long way, and it can already be applied to tackle problems and learn similar to the way people do, for example, by recognizing physical objects in their environment. I've worked for an organization that created headsets which could scan physical industrial plant environments real-time to determine issues. Understanding the context of text is another capability of today's AI systems. And since these are learning systems, they can become more effective over time by applying knowledge of past data patterns to future conditions. Cognitive analytics is a data-forward approach in that it attempts to make future decisions based solely on the data, as opposed to many companies that make decisions based on gut feel, or in other words, emotions and hunches. Cognitive analytics can reveal connections in different data patterns and collections of data that an organization had not previously considered. Today's intelligent computer systems can uncover unique insights. This leads to a deep level of comprehension of the customer's data and allows a personalized approach where the customer's true needs can be predicted and acted on. The growth of cloud computing has ushered in a new era of data analytics. Now it's not only possible to analyze data after it's been consumed, but you can actually perform real-time analytics by analyzing data as it flows into the system. Microsoft offers Azure Stream Analytics, which is a service that can process data from many different sources, such as IoT sensors, social media feeds, and other applications. Azure Stream Analytics takes advantage of the elastic scalability of cloud technologies to make this possible. As a practical example, Azure Stream Analytics could be used to analyze the data coming from a physical thermostat to determine and send commands to a furnace. Here are some ways that Azure Stream Analytics can be used. It can perform geospatial analytics. For instance, the physical locations of delivery trucks could be analyzed real-time to determine best routes. Important assets, such as gas plants, can be monitored remotely, and Azure Stream Analytics could send out an alert if it determines any anomalies in the incoming data. Real-time analytics can be performed. For instance, sales information can be analyzed real-time to determine effective personalized advertising. It's great for monitoring telemetry streams, such as IoT sensors. It could search for out-of-bounds values, for instance, on the pressure down an oil well hole. It could even be used to gather analytics on keywords used in a stream of incoming web logs. Now let's talk about how Stream Analytics works. Stream Analytics can be broken down into three distinct parts: input, query, and output. Data can be input from Azure Event Hubs, an IoT hub in the case of IoT device data, or Azure Blob Storage. The query aspect is where the analytics are performed as data flows in from the input, and it's a language based on the SQL query language. Stream Analytics also allows for user-defined functions, or UDFs, which can be written in JavaScript or C#. Event order and analysis windows are important when performing Stream Analytics. Think of events as a stream flowing by, and the query is analyzing chunks of it as it flows. The query language allows for reordering of these events and managing of the time window. Once a Stream Analytics instance has processed incoming data, it may or may not send data as output. The data that it outputs does not necessarily have to be the same as what came in. In other words, Stream Analytics can consume data and either output nothing, output the same data, or output a different data stream. If it does output data, Stream Analytics can send it to downstream services. It can send its data to Power BI to be displayed in streaming data visualizations, or it can send the data to a storage medium, such as Azure Storage, SQL Server, or Cosmos DB. So to review how Stream Analytics works, it either connects to Azure Event Hubs or Azure IoT, or possibly ingests data from an Azure Blob storage instance. The incoming streaming data from these sources is analyzed and possibly modified via an SQL-like query language. The query's output, if there is any, is routed to one or more destinations. This can be a destination such as Power BI, or it may be a storage destination, such as Azure Blob Storage, Azure SQL Database, Azure Data Lake, or Azure Cosmos DB. Now let's take a closer look at the Stream Analytics query language, which allows you to perform complex event processing of streaming data. It has functions for aggregation as well as analytics. This can allow you to analyze such things as rolling averages or the median value of stream data over time. It has anomaly detection functions, so you can alert on anomalies in the data. Geospatial functions allow you to analyze data that contains geospatial information. Pattern matching can help you perform such analytics as determining which web entries have keywords in them. And there is simple SQL-like data manipulation as well. As far as the Stream Analytics service itself, it's a fully managed offering on Azure. It's a platform as a service offering, allowing you to build your own analytics solutions on top of it. Because it's Azure cloud-based, you don't have to provision any hardware, because it's provisioned for you. And because it runs in the cloud, it takes advantage of scalability, so you can perform large-scale analytics. Aside from running in the cloud, you can also run on the edge. Edge computing means running the analytics on a device between the data source, such as an IoT sensor, and the cloud. Because it's run closer to the source of the data, edge computing offers ultra-low latency. Stream Analytics meets strict reliability, security, and compliance standards, so it can be integrated with your mission-critical processes. It's optimized for cost. You pay for the processing you use. And it's reliable. It never drops events. Every event gets processed. Stream Analytics is a secure service. Both incoming and outgoing data is encrypted. When Stream Analytics stores internal checkpoints, they're also encrypted. And incoming data is never stored in a data store where it might be compromised. The stream only ever exists in memory, as all processing is performed in memory. Finally, it's worth mentioning that Azure Stream Analytics is developed on Trill, which is a high-performance stream analytics engine. Stream Analytics is capable of processing millions of events per second. In this video, I'm going to step you through the different data types that are supported by Microsoft's Stream Analytics engine. Now, I'm using Microsoft's own public documentation as reference, and will not only identify the various data types, but also discuss how these data types are represented in JSON as input to the Stream Analytics engine and how they're converted to JSON as output. To get started, let's review what Stream Analytics does. In this diagram, you see that Stream Analytics accepts input data from a source. In this particular example, it's an Azure IoT hub, streaming data from physical devices. But it could be other input sources as well. The Stream Analytics engine processes that data real-time, which we're going to assume is in JSON format. So this input's in JSON. And it outputs some result also in JSON to any number of outputs. Some output examples are Microsoft Power BI dashboards, or a storage medium, such as a database. In this process, the incoming data in JSON must be transformed into data that can be handled by Stream Analytics. The results, which are in Stream Analytics format, must then be transformed to JSON as output. Stream Analytics supports specific data types for its processing, which we'll look at now. So the first supported data type is called Big Int. This is for integers, so any number that doesn't have a floating point. As you can see, Stream Analytics can handle very large and very small numbers. We're talking 2 to the power 63 and negative 2 to the power 63, so very large numbers, both positive and negative. Now, what does that look like in the JSON that comes into Stream Analytics? In this notepad here, I have a JSON object described in JSON. So starting on line 1, we have curly brackets to start the object, and on line 19, we have curly brackets to end. Inside, I have different fields, and each field represents one of these data types. So on line 2, we have a field called Big Int. I just called it that so you can recognize the data type. And you see what it looks like in JSON. It's a number, it's an integer, and it can be large or small. It can be within 64 bits of precision. Now, one thing to keep in mind is that in JSON, if you put double quotes around this, that makes this a string. A string is not the same as a number. So if you want this to be transformed into a big int for Stream Analytics, it has to be a bare number and not have quotations around it. The next data type is a float. Now these floating point numbers can be very large and very small. Again, 64 bits in precision. Now if we go back to the JSON, what does that look like in JSON? Well, on line 3, I have what I call a float, and I have 3.14. It can also be in scientific notation, but this is a standard way to show a floating point number. So in Stream Analytics, if a JSON object comes in through the input and it sees a floating point number like on line 3, it will be transformed into the float data type. The next data type that's supported is nvarchar max. Now this is for strings. Nvarchar means that it can accept a string of any size up to the maximum allowable string size in Unicode characters. So in the JSON, what we have here on line 4 is an nvarchar. So when Stream Analytics receives this as input, it will translate the property on line 4 as a string or as an nvarchar max. When the output is coming out the other end, if there's an nvarchar max, it will be transformed in the output JSON to something like this on line 4. The next one is date time. So Stream Analytics can manage date times, and in JSON they have to be in a specific format, and that's called ISO 8601. It's a specific standard for date times, and you can see it here on line 5 of my JSON. Here's my date time, and it has a year, and then a dash, 4-digit year, dash, 2-digit month, dash, 2-digit day. So this would be April 23rd, 2020. Then the time and the date are separated by a capital T, and it has a 24-hour hour, so that would be 2 o'clock p.m., 14. And then the minute is 45, so this is 2:45 p.m., followed by 03, which is the seconds. And after the dot, after the seconds, is sub-second data. And the Z at the end represents UTC time. So that's the format, and Stream Analytics will also transform any date time internal to its engine to this format when it comes back out as JSON. The next one is a bit. So this represents a Boolean, true or false, or when you're in Stream Analytics, it translates it to 1 or 0. 1 being true, 0 being false. Now in JSON, that looks like what we have here on line 6. Called it bit, and it's either true or it could also be false. The next data type supported is record. Now record is name-value pairs. Now what does that look like? Well, if we go back to the JSON, on line 7 I'm going to expand record, and what we have is it looks like a sub-JSON object with the curly brackets, and there are key value pairs inside, or property value pairs. So on line 8 I have property 1 is the key, value 1 is the value. On line 9, property 2 is the key, value 2 is the value. Internally in the Stream Analytics engine, this would be translated into an object that would have properties. So you could typically access those with a dot operator. And the final data type is an array. An array is a list of values of a supported data type. So that's one of these data types that's supported by Stream Analytics. In JSON, I can show you what that would look like. On line 11, we have a string array. And notice for arrays in JSON, they use the square brackets. So square brackets and then a comma-separated list of values. So we have value. Here we have strings, value 1 and value 2 on lines 12 and 13. Below that, I also have a numeric array on line 15. So it doesn't just have to be strings. You notice that I have numbers here, 1 and 2. You could also have an array of records, so you can get a little more complicated with it. But that's what's going to go into Stream Analytics if you're using JSON as input. And that's what arrays are going to look like on the output as JSON. Now just to finish up here, one thing I'm going to note is the use of the outputs. If I go back to my diagram here, notice that the output for Stream Analytics I've used as an example, and these aren't the only possible outputs, but you could output to Power BI or to storage. Now I want to pick on Power BI for a minute. If I scroll down here to the bottom, this shows what data types are handled by Power BI, for example. Power BI can display on charts and whatnot big integers, floats, strings, date time, bits, but it cannot display records or arrays. They're not supported. So going back to the diagram, when you're using Stream Analytics, you have to be aware of what output your destinations can handle, such as Power BI or a storage device such as a database. So in conclusion, Microsoft Stream Analytics has a set of supported data types. Incoming and outgoing data will need to be transformed from and to different formats, such as JSON, and you need to be aware of the rules and limitations of those transformations. In this video, we're going to review the 5 core storage services offered by Microsoft Azure. I'm also going to demonstrate how to create a storage account in Azure, and I'll show the configuration of various storage services as I discuss them. So first, let's review the core storage services. Here I have them in the public Microsoft documentation. The first one is Azure Blobs. Now, Azure Blobs are the basis for big data. They allow you to store really any type of data. It's any type of file, such as PDFs, Excel files, pictures, just anything you can imagine. And it allows you access to those on the cloud. The next one is Azure Files. Now, Azure Files also stores files, much like blobs are stored as files, but it's set up to be managed file sharing. So VMs on the cloud or virtual machines, as well as on-premises machines, can connect to and share these files. Azure Queues is a message storing facility, and the way that this works is, think about lining up for the movies. The lineup for the movies is first person into the line is the first person out of the line. And this manages data in the same way. An Azure Queue accepts data and it queues it up so that the first piece of data into the queue is the last piece of data out. Azure Queues are really good for moving data in between services without actually tying the two services together, making them dependent. Next, we have Azure Tables. So Azure Tables is like tables in a database, but they support NoSQL. And if you're not familiar, you may be familiar with relational databases like SQL. Relational databases have schema that are well defined, such as tables and databases and the fields in those tables. NoSQL is schemaless. In this case, it stores JSON files, and the JSON files, each JSON file can have any property you want. Finally, we have Azure disks, and these are just disk volumes that you can attach to a virtual machine in Azure. Now what I'm going to do is I'm going to create a storage account in Azure, and I'm going to show you not all of these. We're going to skip the Azure disks, but I'm going to show you how Azure blobs, Azure files, queues, and tables are generally set up. So let me go to Azure here, and I'm going to click Create a Resource, and I'm going to just type Storage, and that will bring up some options, and we want Storage Account. And click Create. Now I need to find a resource group or create a new one. I already have one created called Storage, so I'll just choose that. Under Instance Details, I have to choose a storage account name, and it has to be unique. So I'm just going to go Test226. That happens to be unique. And then I'm going to hit Review and Create. And I'll click Create. Now that's going to create my storage account. I'm just going to pause while that happens because it may take a bit. Okay, so that's complete, and I can click Go to Resource. And now here is my storage account. Now, a neat thing I can do is on the left, there's an option that's called Storage Explorer. If I open that up, here I can manage blobs, file shares, queues, and tables all in the same storage account. So I'll right-click on blob containers and hit Create Blob Container. A container is like a folder for blobs. So under New Container, I'm just going to call this My Blobs. And I'm going to do something so I can demonstrate to you. I could make these private, which means that you need a special key in order to access them. But instead, I'm going to make my blobs anonymous read access for blobs only. What that will do is it'll allow me to show you how they're accessed via URL. So it says successfully created storage container. And you see on the left I have under blob containers my blobs. So if I click on that, I get a management application here. And at the top on the menu, I can upload my blobs. Now you can do this programmatically. You could have a service that uploads to this blob storage. But what I'm going to do is I'm going to manually choose a file under Upload Blob. And I'm going to go to my own drive here. And under Demo, I'm going to choose a Download JPEG. This is a JPEG that I have set up. So I hit Upload. And you'll notice that in my list, I now have the JPEG downloaded. If I double click on it, I can download it to my machine, which I already have. Now, another interesting thing, if I right click on that blob, remember a blob can be any type of file. If I right click on it and I choose Properties, I can see that there's a URI. Partway down the properties here, there's a URI. Now, if I copy that URI and I just go to a different browser, open up a new tab on my browser, and go to that URI, you see that I can see the picture. So on the cloud, on the web, I can open up that blob and access it because I said that it's public. If it was private, I would need a special key to do that. But basically, services can access the blob through those URIs. Now, the next thing we'll look at is file shares. So if I right-click on File Shares, I can go Create File Share. And under New File Share, I'll give it a name, My File Share. I can set a quota. I'll set it to the maximum of 5 gigabytes. And there are different tiers. Tiers is just the performance of accessing that data. So transaction optimized would be the fastest. Cool would be the slowest, but it would be cheaper. I'm going to hit create that file share. Now, if I just refresh this and I go under file shares, I now have my file share. And just like blobs, I can upload files to this file share. The difference between blobs and the file share is that I also have options to connect, if I look under more, I can connect a virtual machine to this. So on-premises machines and virtual machines can be set up to access whatever files I put in this file share. So it's a full Windows file sharing system. Now the next one we're going to look at is queues. So on the left under queues, I'm going to right click and hit create queue. And I'm just going to simply call this my queue. OK. And I'll click on my queue on the left. Now what a queue does is it accepts messages, which is data, and it queues it up so that the first message in is the first message popped off. And you can do this programmatically. This is often how services interact. Service A, when it wants to send information to Service B, will put messages on the queue, and Service B will then pop the messages off the queue to read them. This is a nice way of them to communicate because then they're not tied together. They can work independently and the queue is the middleman. So if I click Add Message, here in this interface I can just type a message text. So I'll type this is my first message. You see that it has an expiration, so it'll stay in the queue until it's popped off or until the 7 days expires or however I set this. I'll just leave it at 7 days. Hit OK, and you see my queue on the screen and it has one message in it. Now, if I add another message, and I'll type for the message text, this is my second message, and hit OK. Now I have two messages in the queue. Now, like I said, these go in, first out. So the first message I put in was this is my first message. The second message was this is my second message. Now, popping the messages off the queue is dequeuing the messages. So there's an option in the menu here, dequeue message. I'll click that. It says, are you sure you want to dequeue the first message in the queue? I'll click OK. And you see that it's popped off the first message. So queues can only be read first in, first out. And if I dequeue the message again, I pop off the second message. So again, queues can be used for services to interact with one another. Now let's take a look at tables. So I'll right click on tables and hit create table. And again, I'll call this my table and hit OK. Now if I click on my table on the left, this allows me to query just like a traditional database. I can add entities to my table. And as I've mentioned, this is NoSQL. The fields are dynamic. For instance, you do need a partition key and a row key, but I can also add my own properties. And you notice I can give any name I want. So this could be property 1, and this is value 1. And I'll add another property, property 2, and I'll give it the value, this is value 2. Now when I hit insert, there's now a new record in the table, and it has partition key, row key. It automatically adds a timestamp of when it was created, and it has two fields, property 1 and property 2, with my values in it. Now to show you the NoSQL feature, because if this were a relational SQL table, then these would represent the columns or the fields. So the fields would be set. In other words, every record in a table in a SQL relational database has the same fields. But with NoSQL, every record can have its own fields. So if I click Add, for this second entity or record, I can totally change it by removing the properties and adding new properties. So this is new property 1, and this is, I'll just give it a value of say 1, 2, 3, and new property 2, and I'll say it's 4, 5, 6. Now if I hit insert, so now you see that there are more column headers because now the records or the entities in the table have different fields. Notice that the first entity does not have a property 1 or property 2 because that's the one I just entered. It's the latest one, and it only has new property 1, new property 2 values. Whereas The second one has property 1 and property 2 values, but null for the fields that it does not have. So NoSQL tables are very useful in that they can store dynamic data in which the fields are not known ahead of time. So in conclusion, Microsoft offers a suite of 5 core storage services that allow management of data in the cloud. You need to select the appropriate storage for your use. In this video, I'm going to demonstrate how to set up an ELT, or Extract Load Transform pipeline, in Azure, using blob storage as a source and Azure Data Explorer as a destination. So just to review this, I have the pipeline on the screen here, and going from left to right, we're going to have blob storage, and we're going to write a JSON file to that blob storage. And that JSON file is going to be extracted, and it's going to be loaded into Azure Data Explorer. So the data that's loaded into Azure Data Explorer is going to have the exact same fields and values as what was in the JSON file of the blob storage. So in other words, there's no transform that goes on between blob storage and Azure Data Explorer. The transform, which is the T part of the ELT, is going to take place during the query. So every time we query Azure Data Explorer for the data, we're going to do a specific transform on it to put it in the format that we want. So let's take a look at how you do that. So I'm just going to go to Azure. And in Azure, I already have a resource group set up called ELT. And inside ELT, I have 2 resources. One is a storage called ELT Storage 1, and that's my blob storage. And the other is my Data Explorer, ELT Data Explorer. So let's go to ELT Data Explorer to start. Now what I'm going to do is I'm going to set up the destination database. So on the left, I'm going to go to Databases, and I'm going to click Add Database. And database name, I'll just call TestDB. Okay, so my database is created. And if I click on the database and open it up, I'll click on Query. That opens up a query grid for me. Now what I'm going to do is I'm going to first create the table. I'm going to create a table called Test Table. This is my destination table. And it goes like this. .create table test table. It has 3 fields. Timestamp, which is a date time, value 1, which is an int, and value 2, which is a string. Now this is exactly the fields that are going to be in our JSON object. So I'm going to click Run. And at the bottom, in the results, I've created my test table. So if I open up TestDB on the left, I see my test table with my 3 fields. The next step is to create the mapping for the ingestion. This is copying the data from the blob storage to this table. So it says .create table test table ingestion JSON mapping, and I give the mapping a name, test mapping, and I tell it which columns to map from the JSON. So the $dot paths are the JSON path, and column is the column to put it in. So the first one comes from the timestamp field in the JSON to the timestamp column in the table. The next one comes from the value 1 field in the JSON to the value 1 column in the table. And the final one comes from the value 2 field in the JSON to the value 2 column in the table. So they're mapped directly. Click Run, and that creates my test mapping. Now on the left, I'm going to go to Data Ingestion under Settings, and I'm going to create a data ingestion. This will connect us to the blob storage. So I hit Add Data Connection. I choose blob storage. I give it a name, and I'm just going to call it Test Connection. So my storage account is the ELT storage resource that I showed you. The event type is every time a blob is created, it's going to run this ingestion. Under Filter Settings, I tell it where to look for the blobs. So under Prefix, I happen to have a container called Test Blobs under Containers. I'll fill that in. The suffix is .json because I'm looking for JSON files. Click Next. Now under Ingest Properties, I have given my table name for my destination, and that's my test table that I just created in the query window here. Data format is JSON is what I'm ingesting. and the mapping name is the map we created with our query test mapping. Click Next. It'll just validate that, and I'll click Create. So this will create our connection between blob storage and our Data Explorer. Now that's going to take a little bit because it's creating some resources, so I'm just going to pause and come back when it's done. Okay, so that's complete, and now I can go back to my resource group. So now what I'm going to do is I'm going to go to my storage, ELT Storage 1, and I'll go to my blob container under Containers, open Test Blobs. Now recall that we've set this up so that whenever I create a blob in this Test Blobs container, it should ingest that and send it off to Data Explorer. So I'm just going to hit Upload, and I have a blob here just for that purpose. I will upload it, called test.json. Now I just want to show you quickly what's in this JSON file. You'll see that this has the requisite fields. It has timestamp, it has value 1 as an integer, and value 2 as a string. That's exactly what's expected. So now if we go back to the resource group and we go to the ELT Data Explorer, shortly we should be able to query and see that record. Now I will say that this sometimes does take a few minutes because it takes a few minutes to ingest, but I will query and see if it's there. Okay, so now when I query, I'm getting the row that came from the JSON. You see the timestamp, value 1 is 123, and value 2 is this is a test value. Now if we go back to our pipeline, just recall how this is supposed to work. So we got those 3 fields from a JSON file in blob storage. It got extracted and loaded without change into Azure Data Explorer. So we see that in Azure Data Explorer, I have the timestamp, value 1, and value 2. Now the part that we're missing is a transform, which in ELT is after the fact. It's after the data is already in the destination. When we query, we can transform. So I'm going to propose a transform to do on the query, and what I'm going to do is the following. What this does is it takes a test table and it transforms the field value 1 to be called value, and then it only shows timestamp and that value. So it drops value 2 and it renames value 1 to value. So if I run this, you see that now I have my transform. Timestamp is there and the value is 123. So in conclusion, I've shown you how to take a JSON file in blob storage, extract it and load it into Azure Data Explorer, and then perform a transform on the query. And this is an example of the ELT pipeline. Now, some interesting things about the ELT pipeline is that it is very flexible because you can change the transform anytime. You have all the data that was originally in the source in the destination, so you can perform any transform after the fact. So it's really good if you have a dynamic transform and you're not sure ahead of time how the data is going to be transformed. Now the downside here is that every time you query, you take on that extra work of transforming. So it's heavy on the query end as far as performance. In this video, I'm going to show you how to use an ETL or Extract Transform Load methodology to copy data from blob storage to Azure Data Explorer. So let me step you through the methodology. We have a blob storage, and I'm going to write a JSON file to that blob storage. That JSON file is going to be extracted, and when it's being extracted, it's also going to be transformed. Now I'm doing the transform via a mapping to Azure Data Explorer, in which we modify the columns that are written. Now more complex transforms can be done with tools such as Azure Data Factory, but this is just a simple example. Now what happens is that is loaded into a temporary table in Azure Data Explorer, which is then loaded into the permanent storage of Data Explorer. So the data that is written to Azure Data Explorer is actually already transformed from the original. So when we use Custo and query the Azure Data Explorer, we're going to see the transformed data. Now let's go to Azure and see how this is done. I have an Azure Data Explorer cluster, and I have a storage account which has a blob container in it. So let me first go to the Azure Data Explorer cluster. And what we're going to do is we're going to set up the table that's going to receive the data. So in my Azure Data Explorer cluster, if I click Query on the left, I get a query window. So what I'm going to do is I'm going to create a test table. And here's the query for that. I'm creating a test table. It has two fields, timestamp, which is a date time, and value, which is a string. I'm going to run that. And we see that that's succeeded at the bottom. So I have test table on the left with my fields. Now what I'm going to do is I'm going to set up the mapping. And if I go back to our original diagram, we've set up the table that's going to receive the load. And I'm going to set up the transform or the mapping that's going to copy the extracted data to Azure Data Explorer and transform it. I create an ingestion on test table, and the mapping is called test mapping. And what it's going to do is it's going to map to the column timestamp in the table a path into the JSON that's read of $.timestamp. So it will take the contents of the timestamp field in the JSON, is what the path is, and copy it into this table column called timestamp. Secondly, and here's where the transform takes place, is the JSON is going to have a field called value1. And I'm going to copy that into the table column value. So that's a transform. The columns are not going to be the same in the test table. And finally, there is actually going to be a property in the JSON called value2. And I'm not mapping that at all because I don't care about that value. So that's our transform, is we're not copying one of the fields and we're renaming one of the fields from value1 to value. And it's created the test mapping successfully. Now the next thing we're going to do is we're going to set up the connection between Azure Data Explorer and the blob storage. So on the left, I'm going to go to Databases, and I'm going to highlight my TestDB, and I'm going to click on the left under Settings, Data Ingestion. And then to the right, I'm going to click Add Data Connection. So this lets me set up a data connection to a blob storage. Select connection type is blob storage. The data connection name, I can give it any name, so I'm just going to call it test connection. And storage account subscription is my free trial. Storage account is the account that I already have set up. It happens to be called test226. That's my storage account with my blob storage. And the event type is the event that fires the copy into Azure Data Explorer. So every time a blob is created, it's going to fire. Under filter settings, I want to only get the blobs that are in my blob container. And you will see that my blob container happens to be called my blobs. And the suffix is .json because it's JSON files. And I'll click Next. Okay, so now I have to enter the information about my table. So this is the table in Azure Data Explorer that we just created. So it's called Test Table. The data format of what's being read is JSON. And the mapping name that we just created is called Test Mapping. Next. So that's my data connection defined, and I'm going to click Create. Now that may take a few seconds, so I'm just going to pause. Okay, so that's complete. So I'm going to go to my storage account, test226, and I'm going to go to my blob containers. And here is my container called My Blobs. I'm going to open that up. So what I need to do, if you recall, I set up the Azure Data Explorer so that the connection would be fired on blob created. So I need to upload a blob. And I'm going to upload a test.json blob that I have. That's uploaded. I just want to show you the contents of this blob. You'll see the contents of this blob has a timestamp. As I've mentioned, it's the same name as the timestamp in my table in Azure Data Explorer. It's got a value 1 field, which remember we're mapping to a field in the table called value, which is our transform. It's also got a value 2, which we're completely ignoring, and we're dropping that in the transform. So we're not transforming that into the data in Azure Data Explorer. So now that I've downloaded that, it should automatically run the ETL that we've set up and take it into Azure Data Explorer. So let's go there and find out. Go to my cluster, and we'll go to query, and I'm going to just run a query to get the contents of test table. And you can see at the bottom here that we can now see the records, so it has been imported in. So just to review, let's just take a look again, and what we've done here is we've set up a mapping between blob storage and Azure Data Explorer, so that every time a blob is created in the blob storage, it's automatically extracted, transformed by a mapping, and then loaded into Azure Data Explorer. Now, one of the useful features of ETL, or Extract, Transform, Load, is that the transform is done before the query. So when you query Azure Data Explorer, you don't have to transform every time you query. What I mean is that if we go back, every time I hit run, the data is not being transformed again and again from the blob format to the new format with the value instead of value 1. Because that transform has already been done, and this is what's written in the actual table. Now the downside is that the transform is only done once, and so you can never change it. So for example, from Azure Data Explorer, I can no longer query for value 1 or value 2 of the original data in the blob, because the data has already been transformed into something different. So in conclusion, I've shown you the ETL process from a blob all the way to Azure Data Explorer. So in this course, we've examined the core concepts of data analytics. We did this by exploring Azure Data Explorer and using it for data visualization, data reporting with data analytics technology, SQL Server reporting services, recognizing data chart types and analytic techniques, how stream analytics work and their data types, Azure Core Storage Services, and using ELT and ETL processing. In our next course, we'll move on to discuss relational data workloads, indexes, views, and delivery models.